Okay. So, many moons ago, long before our exam, in the before time, we were talking about passive transport. So we're going to spend the rest of today just wrapping this up. So remember, actually let's use, I guess, this. Passive transport overall has a goal to move down gradient until we reach equilibrium. Okay, that's everything that has to do with passive transport, right? So diffusion did this. Okay, and it did this with small molecules. Okay, we talked about facilitated diffusion or facilitated transport, which did this with larger molecules using protein channels. Right, this guy. Right, so remember the key here is we're always moving down our concentration gradient. So we're never using ATP. So right before, in the before time, we had gotten to osmosis, but I opted not to touch it because it's a little bit bigger of a concept. Okay, so now we're going to touch it. So osmosis is still diffusion. Okay. It's still free. And its goal is still equilibrium. Okay. But it does a little mind-bendy action on us. Okay. Because instead of actively moving the solutes around, okay, salt, sugar, carbon dioxide, okay, osmosis is moving the space around, okay, water. Okay, so it kind of messes with our head a little bit. Okay, our goal is still equilibrium. Okay, but we need to continually remind ourselves that when we're doing equilibrium, our equilibrium is of the solutes and not the water. So I like to think of this as the last resort passive transport. Okay, so let's look at the example we have on the right-hand side here. So in our example, okay, we see that we have a high concentration of sugar on the right side and a low concentration of sugar on the left side, right? So the right-hand side needs more elbow room. Okay. Now, in this particular situation, what happens in these situations is that for one reason or another, our sugar molecule isn't able to cross the membrane. Okay? And this would be something I would tell you in a question. All right, so it would start out by saying, sugar cannot pass the plasma membrane. All right, and this is not something I would ever make you guess. Okay, so that puts us in a rough situation, because normally we would say sugar just wants to go down its concentration gradient, and it would move from high to low or right to left. Okay, but it can't do that. We still want to go to equilibrium, however. So what osmosis does is if we can't let our solutes or our people move to a place where there is more chairs to sit, then what we're going to do is take the chairs, the water, and move the water into the space where there's too many people. So that's what we've seen here, and that's how we've created equilibrium. Okay, is we've taken all of the extra chairs from our low concentration side, and we've added them to the high concentration side so they can spread out. Okay, they have more space now. Okay, so we've moved water from the open side to the smushed side. So now everybody has an equal amount of space. Okay, so it's like taking chairs from an empty classroom, moving them into the crowded classroom so everybody can sit down now. Okay, so notice we look at this image on the right-hand side, we're at equilibrium now, right? Everybody on that right-hand side has equal elbow room. And everybody on that left-hand side has equal elbow room. We just did it in a weird way. Does everybody see what we did there? Okay, so this is what I mean about being mind-bending. So we're moving the space instead of the people. So I like to think of it as adding chairs. Okay, any questions about what we've done here? Okay. So remember that you have your lab exam coming up next week. The recitation packets that we did last week has a couple examples that do this, since they make really good practice. So let's look at osmosis as it applies to cells. Okay. So when osmosis, or water and solute exchange, works with cells, okay, so we're thinking plasma membranes, then we call it tonicity. Okay. So I'm going to end up going through these one by one, so don't panic and like slam right, don't worry. So we have three different situations that can fundamentally occur when we're thinking about cells. So really we're thinking about, if I'm a cell in an environment, okay, how does the concentration of salt inside my cell or inside my body compare to that of the solution outside? Okay, so imagine dropping a cell in water. Okay, how does the solution of the cell compare to the solution of water? That's what we're talking about here. Okay, so I'm going to flip back and forth between this slide and a blank slide on the next page so I can draw these situations out. Okay, so let's start by looking at this first one, isotonic. Okay, where we would consider the inside and outside equal. All right, so here's my term. Okay, so I like to think of isotonic, like if you're a math person, no, think like isosceles triangle. I've got another one, don't worry. Okay, so I am a happy little cell. Okay, so here are my solutes, 1, 2, 3, 4, 5, 6, 7. Okay, that one looks like it's escaping, but for the sake of argument, all right, I've got the same amount of solutes inside my cell as I do outside my cell. So, what does my solute movement look like? But, say again. Equal exchange, good. I'm at equilibrium, right? Okay. Since we're talking about osmosis here, the water is also going to be equal exchange, right? So I don't have anything to dilute. Okay, so I have no net loss or gain. Okay. So I am happy. I so happy. Okay, so my cell is going to maintain its shape, it's happy, and living its best life. Isotonic. Okay. The next one on our list is hypertonic. Okay. This one says that the outside solution should be of a higher concentration. All right, let's make that happen. I'm going to start at least with a happy little cell. Okay, but then we said that the outside solution is supposed to be higher, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh dear. Okay, so what is my solutes going to do? Where's the concentration gradient for my solutes? They're going to go in. Okay, so I'm going to be a salty little guy. Okay, which is something that happens. Think about like cured meats. A tasty little guy is what I am. Okay, what's the water going to do? It's going to go out. That doesn't sound good, right? So in vain, all the fluid inside my cell or my tissue is going to leave in an effort to dilute the area around me. So I am no longer happy little cell. I am now shriveled little cell. Okay, so the word hyper, think like hyperactive, okay, means a lot. So this is referring to the fact that there's a lot of solutes on the outside here. And the way I remember this one is the E here for hypertonic looks like a shriveled cell. All right, we got one left, and so we've had same, higher, so that leaves us one left, right? Hypotonic. Okay, so hypo, think hypo is low. Okay, so our outside is going to be lower. All right, so let's start with our happy little cell. I think we all know that this is not going to stay a happy little cell. So here's our, I don't know why that was bigger, our happy little cell. What direction are the solutes going to go? Out, down its concentration gradient, right? More problematically, direction's the water going to go? In. If we thought a shriveling cell was problematic, this is going to be a serious problem here. So as all the water rushes in, okay, just like overblowing a balloon, bigger, 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 kaploosh. Okay, these cells literally explode or lyse as they overfill with water, and it stretches their cell membrane so thin they burst. Okay, so there are certain diseases, cell age that can do this. You can do this to yourself if you drink too much water. Okay, there was a game a while back to like win a PS3 or a PS2 or something like that, where people like drank gallons and gallons of water and one kid died. He dry drowned doing this. Yeah, it was a whole thing. Okay, this is what you do to yourself. All right, so the way I remember this, remember hypo means low, and this O here, okay, we picture it's like a big swollen cell. Okay, so these are all form of osmosis in cells, aka tonicity. Looks better when I draw them, right? Okay, any questions about this? Okay, this is the last bit of passive diffusion we're going to talk about. We're slimming down the membrane transport. All right, so the very last thing I'm going to talk about it all when it comes to membrane transport is active transport. I'm going to lump this all into one thing. So you're going to see active transport has a few other diddly details. We're just not going to talk about it. Okay. So the only thing I want you to know about active transport is how it generally differs from passive transport. Right. So remember that passive transport really focused on moving whatever it was moving, right, sugar, salt, whatever, down its concentration gradient. And because it was moving downhill towards equilibrium, it was free of charge. Okay? Active transport does the opposite. Okay, so it's moving substances against a concentration gradient. Okay, we're going against the flow of traffic. Okay, and because of that, we're going to use ATP, the currency of the cell. Okay, this allows cells to have a different concentration than the space around them, and this is super common. So if we think back to our tonicity argument, okay, if I'm a happy little cell, Okay, but I'm a happy little cell in fresh water. Okay, my happy little cell has to have some solutes inside me, right? My heart has to pump. I have to have food. Things are inside me. Okay, fresh water pretty much has none, right? That's what makes it fresh. Okay, there's no salt or anything in it. Maybe we have like one here or there. So by the very nature of me being a fish or a cell living in fresh water, everything wants to leave my body, and I'm gonna want to explode. That's like death. So that's bad. Active transport is a way we keep that from happening. So, dollar bills, yo. Okay, we just pay to keep my stuff in and the water out, right? We're moving them against their natural gradient. Okay, I'm going to pay to truck them back out. Okay, so this happens a lot. So for my heart to pump, okay, I have to use calcium. That's a salt. Okay, but I use a lot of calcium. There's more salt in my heart than there is in the surrounding environment around my heart. Okay, but I don't want the salt to leave my heart. I kind of want it to keep pumping. So I pay. I use ATP to keep bringing salt into my heart so it can keep beating. But that's okay. I kind of want my heart to work. Okay. This cell here doesn't want to explode. That's okay. So it's going to pay. It's going to use ATP to pump water back out of it. Doesn't want to explode. So these are active processes. Okay, I'm going to work against their equilibrium gradients, and we're going to pay ATP to do it. I have a video for this, but the sound in here is not working. So I'm going to pull it from the PowerPoint, and I'm going to post it on eLearn, where the video or the sound always works for you guys. So I will get that in this afternoon. It's very frustrating this morning. So we're going to go ahead and stop here. I will post a video, and then we'll start Friday with a Menti.